Alrighty, welcome to Module 4, Lesson 4, Percent Increase or Decrease. A wonderfully helpful lesson and one whose concepts we'll need to probably visit again and again because it could be tricky. It could be tricky, but very, very useful in our daily lives, absolutely. Okay, so with no further ado, let us begin. Here is our opening exercise. Let me see what I did here because I did all the animation already. Okay, all right, I better read it first then. So Cassandra likes jewelry. Okay, she has 5 rings in her jewelry box. Here's her little rectangular jewelry box. And so in the box below here, let's go ahead and sketch Cassandra's 5 rings. If you want to pause right now and go ahead and do this, be my guest. If not, just continue with me. You'll probably make much nicer rings than I am about to. Okay? So here are my rings. 1, 2, 3, 4, 5. Okay, 5 rings. There's Cassandra. She has 5 rings. Very dull looking except for one. Pretty nice diamond there, second from the left. Okay, so what we're going to do here now is we're going to go ahead and draw a number line diagram relating the number of rings as a percent of the whole set of the rings. And you can remember our double number line diagrams. Okay, we're going to make it look a teeny weensy bit different this time. Okay, so I'm doing this because when we talk about this percent and increase or decrease, and we're not going to venture into any negative numbers here. We can put an end over there because we can't have any less than 5 than 1 ring. Could have half of a ring, I guess, but for any useful purpose, anything less than 1 ring is not worth much of anything. Okay, so with this right now, so that's why we're going to put that little wall there to the left. Okay, and if we go ahead and create, just label, we have the top line is the percent, and again, you've seen this before, we've done this before, and the bottom is the number of rings, and then we can see right there we have at 5 rings, that is 100%. Okay, and you can see I've left a little bit of room to the right. Okay, because as we had mentioned, you can go greater than 100%. Okay, and that's one of the big rules or big lessons. Hopefully, everyone's going to know by the end of all of this is that yes, indeed, we have greater than 100%. We have thousands of percent. Okay, we cannot go less than. If you lose, you cannot lose more than 100%. Okay, you can't lose more than 100% of anything, but you can gain hundreds and thousands of percent. Okay, so pretty unlimited on the upside, but limited on the downside. Okay, now losing 100% of your money, for example, is very terrible. It doesn't get much more terrible than that. The truth is, you could owe someone money that you don't even have. And that's the worst of the worst. Okay. Anyway, let's keep going because I can go off on a tangent here. All right. So C asks us here, what percent is represented by the whole collection of rings? What percent? Of course, and that is an easy answer. Of course, that's 100%. Okay, because 100 is our whole. Okay, and that's that number there, whole, 100%. Okay. And now, here's a question, though, the question of the day, or the question of the moment. What percent of the collection does each ring represent? Okay, so each ring has a percent itself that it's worth. Some of you may know this right away. I'm so happy for you. Skip along if you need to, okay? Those of you who want to stick around, please do. Okay. So what I do, and again, we're just trying to represent this visually, especially to those of you who may have a little bit of difficulty still wrapping your head around this idea of percentages, okay? So I'm going to go ahead and split this double number line diagram up into 5 sections, both top and bottom, which makes sense because I have 5 rings, Okay, so 1, 2, 3, 4, 5. And now each one of these rings, okay, if I split the 100 into 5 pieces, I can see that each one of them is worth 20. Okay, so very simply, I did a little division, and all I had to do actually was divide 5, oopsie daisy, okay, is divide this 5 here, okay, this 5, I need to do, sorry, divide 100 by 5, okay, and that would be 20, okay, so 20%. Each one ring represented 20% of the whole, okay? Okay, so let's move on to continue with Cassandra's example here. So Cassandra's aunt said she will buy Cassandra another ring for her birthday. Okay, if Cassandra gets the ring for her birthday, what will be the percent increase in her ring collection? Okay, you know, a good word here that we know it's going to mean increase, of course, is another. Okay, she has another ring for her birthday. If she gets her ring, what will her the percent increase in her ring collection? Now remember, we started this collection off with 5. So think about the question before this one. Okay, so before this one, if we go back and we just take a peek at where that all ended, okay, right there, we can see that each one of our rings, each one of these rings, this 5-ring collection, was worth 20%, okay? So if we think about that first, and then we just move forward here, okay, and go ahead and, yep, there we go. Just think about the question before this one, okay? So what percent is represented by one ring, okay? We answered that question, and that was 20%. So each ring in this collection is worth 20%, okay? So we begin with 5, we began with 5, and then we would end at 6, okay, if Cassandra's aunt bought Cassandra this this one ring. Okay, so she increased 1. It was an increase of 1 ring, okay? So from 5 to 6, that was 1, okay? And what she did, she started at, or her original number of rings, and again, we're going to talk more about this as we move along in this lesson, but that original number, this is really important, this idea of the original number being of utmost importance, was 5, okay? So we are comparing the increase, which was 1, to the original number, which was 5, okay? And that's where we get this 1 over 5 here, okay? So 1 over 5. And then if we go ahead and do the math there, we see that 1 over 5 is the same as 20%, okay? So her ring collection will increase by 20%, okay? Okay, so here we go. Let's talk about John now. John is doing his trading cards. Okay, so now again, John increased his trading card collection by 5 cards. Okay, he originally, here's that word originally, had 15 cards. What is the percent increase? Okay, and they're asking you here to use the equation quantity equals percent times whole, and then justify your answer using a numeric or visual model. Okay, I'm going to try. I'm not sure if I don't remember if I even used the numeric or visual model because, I don't know, I was a little tired of it. But anyway, yeah, so let's go ahead and do this. And again, keeping in mind now when we're reading through these problems, you know, just paying attention to those key words. And like I had said, you see that word originally or original is very, very important. Okay, and there we go. Yeah, just underlined that. Okay, so there it is. Q equals percentage times whole. Okay, and we're going to look at this a little bit differently in a minute. Same idea, same end to the means, but just some different terminology or extra terminology. Okay. Okay, so the Q in this case, or the quantity, okay, and that's usually the amount of increase or decrease, or the new amount after the increase or decrease, and again, that's something we'll wrap up with. But in this case, the quantity we're talking about is 5. How does 5 compare to the original, okay, and that's the original, okay. So how does 5 compare to 15, okay? What percentage of 15 is 5, okay? So what was this increase, okay? We'll just keep moving that along, and then of course 5 equals 15p, always turning around, same as p times 15, okay, and then there we go. So you work it out again. I'm just multiplying 5, and hopefully this is natural for you right now. Multiplying 5 by the multiplicative inverse of 15. We know this is going to become just a single p. Okay, and then when I do that, 5 over 15, which is the same as 1 over 3, not, as we have found out in the past, the prettiest of percentages, because 1 over 3, and one we should get to know really, really well, is 33 and 1/3%. Okay, so 33 and 1/3%. Okay, so let's go ahead and try to visualize this thing. Okay, again, we have our double number line diagram thing. Okay, and again, we have 100% on top, from 0 to 100%, 0 to 15 cards. Okay, and again, splitting this up now, instead of, well, yeah, it's really easy to split these cards up into groups of 5. And again, you could see there are, 4 groups of 5 right there. I'm sorry, 5 groups of 5. Wait, 1, 2, 3. Wait a minute, 5, 10. You have 1, 5, 10, 15. Sorry, 3 groups of 5. 3 groups of 5 there. Okay, so each one of those, if I'm splitting that up into 3 different groups, I know each one of those is going to be 1/3. So that you can see that 5 represents 1/3 of the cards. Okay, if I added another 5, which would bring us up to 20 over here, I can see I'm just adding another 1/3, which of course is, whoops, should go back there. 1/3 of which of course is 33 and 1/3%. Okay. Alrighty, here we go. Now next. So, suppose instead of increasing the collection by 5 cards, John increased his 15 card collection by just 1 card. Okay? Will the percent, this is the important part here, will the percent increase be the same as when Cassandra's ring collection increased by 1 ring? In example 1, why or why not? And again, maybe for some of you this may seem like an obvious answer, but I'll tell you the honest God truth, this is something that really can confuse kids, because they'll see here, well, hey, his is going up by 1, and Cassandra's went up by 1, so yeah, they went up by the same. But this is what makes percentages so useful and so wonderful, is that they take the mystery out of this, okay? And if we understand percentages, so you will never get these questions wrong. Okay, so let's go ahead and just map this out. So here we have John, we have Cassandra. Okay, now John started with 15. Cassandra started with 5. Okay, and that should be keying you into the whole thing right now. They started off with different numbers. Okay, 5 rings versus 15 cards, playing cards, trading cards. Okay, but they both added 1. That was the same. Okay, that was the same. The idea that they added 1. Okay. All right, and they ended. But now look at, John ends with 16. Cassandra ends with 6. Okay, again, these are different numbers. All right. And of course, they both started with, added 1. And they started with different numbers, ended with different numbers. Okay. So if we look at John, his 1, okay, and this is what he added, is equal to p times 15, okay, because the percentage times what he started with, the original amount. Okay, with Cassandra, though, it's 1 equals p times 5, and we can see right now, right away, we don't have to do any other work, actually, at all, to answer this question, yes or no, okay, because the answer is very, very obviously no. I mean, 1 equals p times 15 cannot be equivalent to 1 equals p times 5. Those are different equations entirely. Okay, So yeah, so there's the question. So if we go ahead and work this out, though, we can go ahead and do it. We can see that, I did this really fast, huh? Wow. Okay. Anyhow, we can see that here. So in John's case, I should probably back that up, huh? Let me go really slow with this here. Okay. So if we look at this here now, we can go ahead and do John's. Okay, so John, we have 1 equals 15p. Cassandra, 1 equals 5p. All right, and we're going to go ahead and multiply, of course, by the multiplicative inverse. Okay, 1 over 15 on both sides and 1 over 5 for Cassandra's on both sides. Of course, we know on the right we're going to get left with p both times. Okay, and at the top. And then we can see that 1 over 15 times 1 is 1/15th. Okay, and with Cassandra, 1 over 1/5 equals p. Okay, so we have, and you can see these are both very different, and you can tell by looking at that, you know that 1/15th is going to be less than 1/5. Okay, so they are different. And 1/5, of course, as we knew before, was 20%, but in John's case, that 1 over 15, or 1/15th, is 6 2/3%. So you can see that John's collection increased by a lesser percentage, okay? A lesser percentage, because 6 2/3% is less than 20%, okay? They both had the same number of items increased by the same. They both got one more item in their collections, but John started from a bigger number. Excuse me. John started from a bigger number, and therefore his percentage was less. Okay? And, okay. All right, well, I got to speed this up a little bit. Okay. So, let me stop that before I start writing here. Based on your answer to part B, how is displaying change as a percent useful? Okay, and I guess I've been talking about this quite a bit already, but comparing by a number increased is misleading unless you pay attention to the amount you started with, okay? And that is really, really important. You can't just compare by the number increased. It's very, very misleading, all right? You have to pay attention to the amount you started with, that original amount, okay? This is why percentage is so useful, okay? It's very, very useful because percentage is always going to give you an amount that is relative to what you started with. Okay, always going to give you that percentage related to what you started with. Okay, here we go. Move on here. We got a little bit of a discussion. Okay, I want you just to consider this question here or scenario. So a waiter is taking 10% off of your total bill as an apology for you having to wait an excessive amount of time for your food to arrive. Okay? So a waiter is taking 10% off of your total bill. Okay? Now there are a couple of ways to look at this or to think about this, and you're going to come to a conclusion as to what you think is more useful to you. What's going to work for you? But let's go ahead. Okay, so there are a few ways to look at this, okay? You can look at this if you're thinking, okay, I have to calculate what my total is going to be. You can look at it in terms of, yeah, I will only pay 90% of my bill, which is true, okay? It's just true because if your waiter is taking off 10%, okay, 10% off, you're going to be paying 100 minus 10, which is 90%. Oops, I thought I had turned it off. I'm sorry. You had to hear me cough. Excuse me. I thought I paused. Sorry. Okay, here we go. All right. So sorry. This is a real human being on the other side of this screen. Okay, so here we go. So instead of his normal 2,500 calories, and again, that's going to be the whole because that's more or less the original. Okay, that was the original. It was the normal amount. Okay, the original, that 2,500. of course, multiplied by the percentage, which we are trying to work out here, and it has to equal 300. Now, that 300, of course, was come across by just taking the original 2,500 or the normal 2,500 and subtracting out his new intake, which is 2,200, and coming up with the 300 calories. Okay, so we're trying to find out, did Ken reduce his calorie intake by 7%? So we're looking at this quantity number, this Q over here, as being the percent, as the amount decreased. Okay, in this case, it's the amount decreased. Okay, so go ahead, if we look at this here, just changing up there, 300 equals 2,500p. And we do our math. Again, I'm not doing any of this on the right side anymore. We're the p value, because it's always going to end up to be p. But multiplying that 300 times 1 over 2,500, a little cross cancellation, equals 3 over 25. And I could really easily do 3 divided by 25, get 12%. I could also look at it like this. I can say that 3 over 25 is the same as 12 over 100. Okay, just multiplying both of these times 4. And that's where I get my 12%. So it looks like Ken reduced his calorie intake by 12%, which is a no-no because his trainer told him no more than 7%, Ken. Okay? All right. So no. Okay, so 300. Now, again, here's another way to look at it. If we know that he reduced his calorie intake by 300, okay, because we can do the 2,500 minus the 2,200, okay, we can just estimate. We can look at, hey, we're trying to find out if he reduces calories by by no more than 7%. Well, I can already know right away that 10% of 2,500, which was his original or his normal calorie intake, is 250 already. Okay, so if I know that he's already greater than 7% just by looking at 10%, okay, then I know he has not done a good job. Okay, he is already over 7%. Okay, just by estimating 10%, which is 250, not even 300 yet. Okay, so I could estimate and I can look at it and I can say, hey, yeah, I know he didn't go 7% or under, but then I want to justify my work by doing all that work. Kind of did this all backwards this time. Okay, let's go ahead and look here. We have this problem that follows here. We have Skylar is answering the following math problem. So the value of an investment decreased by 10%. Okay, we got our decrease here. Okay, the original amount, here we go again, original amount should be the key for you of the investment was $75. Okay, what is the current value of the investment? Okay, current value, original amount, decreased by 10%. All of those key words in this word problem should help us identify our whole and our part, and of course our percentage. So here's part A here. So Skylar said 10% of $75 is $750, and since the investment decreased by that amount, you have to subtract $750 from $75 to arrive at the final answer of $67.50. Okay? Now, Skylar's correct here, okay? That 10% of 75 is 750. But what we're asking here for us to do, for you to do, is to create one algebraic equation that can be used to arrive at the final answer of 6750. Okay? So you got to solve the equation to prove it results in an answer of 6750. Okay, and be prepared to explain your thought process to your computer screen, which is me. Okay, so yeah, why don't you go ahead and pause? We haven't paused yet in this lesson. Let's pause and have you do this right now, based on what we've already done in this lesson, and then come on back. Okay, so welcome back. Now, I am going to just use another another letter here. I want to use C as the current value. And that current value is now our quantity. That's more or less our Q right now. We're going to change that to C just because of the current. It's a current value. And that current value is the actual value after the decrease, okay? Because like I had said, that quantity number could either be the number of the decrease, the amount of the decrease or the amount of the increase, or it could be the amount after the increase or after the decrease, okay? So it could be one or the other. But the original amount is the whole. Now that whole is always going to be that original amount when we're talking about a percent increase or decrease, okay? So here we have our new percent formula here. So C, quantity or current value, equals $75 minus 10% times $75, okay? Now we could do it that way, okay? Is this the most efficient way? Probably not, okay? So we could also look at it as, well, we'll look at it this way first, okay? But yeah, so we are. So we have 75 minus 750, which is 10% of 75, equals 6750. Okay, so we've solved it with that equation. We could also look at it as C equals 90% of 75, which equals 6750, which we could also, of course, instead of 90%, which is 0.9, times 75, and just do our math that way. Okay, so a little bit quicker in that sense to do it. Go back there to do it using the 90% here. Okay, so yeah, so we've proved it with an equation. All right, here we go. So now we're sticking with Schuyler, okay? Now Schuyler wanted to show the proportional relationship between the dollar value of the original investment, which on this table here is X, okay, the original investment, and its value after a 10% decrease, Y, okay? Now, this is what he wanted to do. So he creates this table of values shown, this table right here. Now, does it model the relationship, okay? Because he's looking at trying to relate proportionally the original investment and the value after a 10% decrease. Now, has he done that with this table? Okay, so if we look going from 75 to 7.5, that would mean that Y value there is 10% of X. Okay, so he hasn't actually created a proportional relationship between the original investment and the value, but what has he done? What has he shown here? What relationship is he actually showing? Okay, because in this case, it's always Y equals 10% of X, and that goes, for every value down. Okay, so what he's done is this models the relationship, but it's between the original amount and the amount of the decrease. And can you see that? Okay, because he's created a model here where X is the original amount, and then Y is the amount of the decrease, because that would be 10%. In every case, the Y value is 10% of. I wanted to stop there for a second. I just wanted to see, because 7.5 is 10% of 75, 10 is 10% of 100, 20 is 20%. I'm sorry, 10% of 200. 30 is 10% of 300, and 40 is 10% of 400. Okay, so he has indeed created this proportional relationship, but it's not the one he intended to do. Okay. Okay, so what I did here is I went ahead and made a new table, okay, and set it up like this again with our original amounts, okay, the original amount of the investment. All right, now if we were to go ahead and do this correctly, model what he originally wanted to model was a relationship between the original investment and the value after. Okay, now we do it here because $75 after a 10% decrease is going to be 67.50. 100 after a 10% decrease is going to be 90. 200 after a 10% decrease is going to be 180. 300 after a 10% decrease is going to be 270. And then 400 after a 10% decrease is going to be 360. So this table down here, right now, this models what Schuyler had intended to model. Okay? All right, so here's an important note just in between parts here. The greatest difficulty encountered when finding percent increase or decrease is identifying the quantity or part, as well as identifying the whole or the original amount. Okay, very, very important to identify correctly which part or which number you're going to put on the left side of the equation, so to say, because we know we have quantity equals percent times whole or original amount. Okay, just to know what numbers in the problems go on the left and the right. And the key pretty much are the words that are being used. Okay, and you'll get to know it more and more, better and better. Original amount. Okay, that's going to always give away the fact that that's going to be that whole value. Okay. Anyway, yeah, let's go ahead and have you guys take a stab at this one. Okay. Justin earned 8 badges in Scouts, in Scouts as the Scoutmaster's last report. So he earned 8 badges as of the last report. He wants to complete 2 more badges so that he will have a total of 10 badges earned before the Scoutmaster's next report. Now, if Justin completes the additional 2 badges, what will be the percent increase in badges? Okay? Now, very, very important, again, just like that note I had just mentioned to you, identifying the quantity or the part and the whole or the original amount that goes with this. Oh, darn it! This goes with this this problem. So go ahead and give this a whirl. Try to set this up using that the percent formula. Okay, go ahead and give it a whirl. I'm going to pause and come on back when you think you might have an answer. Okay, so we are back, and yeah, so I picked 2 as the quantity because he wants to complete 2 more badges. Okay, so this is what we're comparing. We're trying to find out what percentage 2 is of the whole, okay, because that's going to be the increase. And again, like I said, that Q value can sometimes be the number increase, or it could be the number or the amount after the increase, okay? And then the whole is 8. Okay, and some of you might have put 10. Very often kids are looking at these, at the bigger the number, that's what the one that has to be the whole, okay? It's not true. It's not always true. That whole is not necessarily always the bigger number, but it is the original amount, okay? Because we said Justin earned 8 badges, and that's where he starts from. He starts from this 8. He wants to get to 10, okay? But he starts from 8, and then he needs to complete 2 more, okay? And so in this case, we have our original amount, which is 8, okay? All right, and P, that's what we're solving for. And again, we have 2 equals 8P, and I do all my division. Hopefully you guys are really kicking it with this one, knowing how to, once you get to this point, there should be no questions after that, okay? Multiplying by the reciprocal or multiplying by the multiplicative inverse, and there you go. So it goes to 2/8, 1/4, and that is 25%. So his increase, he increased his badges. Well, he will complete, if he completes these 2 badges, additional 2 badges, he will have increased his number of badges by 25%. Okay. Now this next part here says B, it asks you to express the 10 badges as a percent of the 8 badges. So go ahead and give that a whirl. I'm going to pause again. And yeah, just express those 10 badges as a percent of the 8 badges. What do they represent as a percent of the 8 badges? Okay, so again, if we put together our percent model, okay, we have 10 equals 8p, and the way we get that, of course, is we have 10 badges now as what we want to compare to the 8 badges, which was our original. Therefore, we have 10 equals 8p, or 8 times the percentage. What percentage of 8 does 10 actually equal? And again, just by multiplying by the multiplicative inverse, we get 10 over 8, which is 5 over 4, which I can extend out. So I could have just divided, 5 divided by 4 here, but I can extend it out to the equivalent 100th fraction, which is 125 over 100, which very easily recognized as 125%, which means that 10 represents 125% when it compared with 8. Okay, so going from 8 to 10, okay, 10 is 125% of 8. Okay, because it's 100% of 8 is 8. Then add another 2. Well, actually, that's the next part of this problem. So this problem asks you, does 100% plus your answer in part A equal your answer in part B? Okay, so 100 plus your answer in part A, which is over here, equal your answer in part B, and that is yes. The answer is yes, because 100% plus the 25% over here gives us 125%, which is our answer here. Because when you look at 10, 10 has 8 in it, which is 100% of 8, plus another 2, which is another 25%, which total is 125%. Okay, here we go. Example 4. Okay, so the population of cats in a rural neighborhood has declined in the past year by roughly 30%. That word roughly is going to play a little part when you see the final answer here. Okay, now the residents, they hypothesize that this is due to wild coyotes preying on the cats. Now the current cat population in the neighborhood is estimated to be 12. Approximately how many cats were there originally? Okay, so I've underlined a few key words. Declined, of course, 30%. So we know our percentage, and we know it's a percent decline or decrease. Current cat population is 12. And then how many cats were there originally? So you can see we're trying to solve for that whole, because that's the original part. Okay. So if we got there, Q equals P times the whole, or the original. Okay, we look at the current as being the Q, okay, because that is the amount after the decrease, okay, because 12, they have 12 right now currently, and that is after the decrease of 30%, okay, and then the 30%, of course, we get, we know that there's a decrease of 30%, okay, so 100% would be the original, so 100% minus the 30%, so now we have only 70% of those original cats left. Therefore, 12 current is going to be only equivalent to, or equal to, 70% of the whole, or the original number of cats. So then we go ahead and we change that 70% to 7 over 10, okay, because that is a lot easier to work with, okay, and you're going to have to decide sometimes what you would like to work with, fractions or decimals. I would really prefer, when you can, to work with fractions because you will see a lot of fractions in the future, and it's something to be very, very comfortable with. But as you can see, I put 12 equals 7 over 10W, which is the same as 70% W, and doing our thing and getting 120 over 7. 17.14 is the answer, rounded to the hundredths place, but of course you can't have 0.14 cats, so our estimate truly would be 17, and of course that estimate, we're only going to have an estimate because you know, we're talking about a rough decline. Okay, here we go. We got example 5 here. We're looking at finding the original amount now, given a percent increase or decrease. Okay, this is a little bit different, probably the more confounding one for students, but it doesn't need to be difficult because we have a formula and we have a process. Okay, so here we go. Lou's math score on her achievement test in 7th grade was a 650. Her math teacher told her that her test level went up by 25% from her 6th grade test score level. Okay? So here we go. So it went up by 25%. What was Lou's test score level in 6th grade? Now we need to be just very, very careful initially. We're looking at went up by 25%, so we're thinking, okay, I just need to, multiply by 25% or divide by 25%. Okay, but let's go ahead and look at this a little bit more closely. Make a little bit of a table right here. So 6th grade we don't know, but we do know that her test scores were 650, was 650 in 7th grade. So actually right now we have a couple of unknowns. Well, first of all, this here, of course, her test score in 6th grade, this is the true unknown, okay, because that's what we're trying to find. We're trying to find that original amount, okay. But I'm thinking some of you are maybe not quite sure as to what to multiply that by, okay, what to multiply that by. All right. So if you look at it, she went up by 100%, okay? But we need to remember her score from 6th grade, okay? We need to remember that score. We don't know it, but we know if we think about her score from 5th grade, that would be equivalent to 100%. So whatever she had in 6th grade, that's the 100%. And then we need to add another 25%. Therefore, we are actually multiplying by 125%. So if you're going to find an original amount, if you're going to go back to the original and you had an increase, you've got to remember it's going to be whatever that increase was, which was 25%, you've got to add another 100% to it, okay? So we are going to have to multiply our answer. So now if we go ahead and plug this in to the Q equals P times W, okay, we know our Q is going to be 650, okay, because that's the quantity, that's the score she has now. That is the score after the increase, okay? Like I said, the quantity could stand for, okay? And our percentage is 125%, okay, or 1.25 times W, which is the original, which is what we're trying to solve for. So I also, and again, just trying to really encourage you to use fractions. That 1.25 W could also be 1 1/4 or 5/4, okay, as well, 5/4 W. So if I go ahead and do that and multiply 650 over 1 times 4 over 5, of course, which is the multiplicative inverse of 5 over 4, okay, I do that, I cross cancel, and I get 520 over 1, or 520 as being her score in 6th grade. Okay, so that would be, we would take, therefore, take 520, and if you multiplied that by 1.25, and you can check it on your calculator right now, you would get 650. Okay, so here we are. We're at the closing page. We're at 45 minutes and some, so let's shoot for getting done in less than 50. Okay, so something to think about. How does a problem's context determine whether there is a percent increase or decrease? The keywords will guide us, okay? And we saw that throughout this lesson. The keywords were our guide when we looked at increase or decrease, before and after, original amount, current amount, all of those things, all of those words will guide us, okay? Now our Q equals P times W. What does the whole represent, okay? In the problems where we have percent increase or decrease, that whole is always going to be the original amount, okay? It's always going to be the original amount. In that case, that does not change, okay? But the quantity aspect of it, the Q, what does that represent? Well, that can represent a couple of things. It could represent either the amount of change, and we saw that quite a bit in the examples that we just did, or it could also be the amount after the change, okay? It could be either the amount of the change or the amount after the change, okay? And we will we'll talk about that a little bit more later on in these lessons. So anyway, here we go. So let's go ahead and just finish this one up right here. So in this little closing portion here, what we want to do is just to have a little bit of practice here in representing which is the whole unit in a problem, because recognizing that whole unit, okay, is really of vital importance, okay? So why don't you go ahead and do that? So what I want you to do is look at it, and like for the first one, it says Mary has 20% more money than John, okay? What in this sentence here represents the whole unit, okay? So there's 1, 2, 3, 4. I'm going to pause right now. You whip those out, and you're going to write right next to it the answer, and come on back and we'll check. Okay, so let's go ahead and look at this here. So if you look at that first one, you know, Mary has 20% more money than John. So John's money is the whole unit, because we are comparing Mary's money to John's money, and she has 20% more than John. Okay, so his is like that original amount, that whole amount, and we will add a 20% to it to get to Mary's. Okay, the next one, Anne has 15% less money than John. Again, that whole than John. John's money would represent our whole unit, okay, 100%. And you can see you're starting to get the idea of the word than, and that's how that helps us out. What percent more money does Anne have than Bill? Of course, that is Bill's money is going to represent our whole unit. And in the last one, what percent less money does Bill have than Anne? And now it is Anne's money, okay? And again, you can see, again, this idea of these keywords that can help to guide us. And in this case, you had that keyword was than. Okay, so here's our lesson summary. We have about a minute to get out of here before 50 minutes strikes, okay? So within each problem, there are keywords that determine if the problem represents a percent increase or a percent decrease, okay? Equations can be used to solve percent problems using this basic equation, okay? Quantity equals percent times whole. You know, again, and in this lesson, we've looked at whole as being more or less the original amount. We talked about percent increase or decrease, and quantity was either amount of change or amount after change. I'm going to make it a big mess here, but if you want to write this down somewhere, you can. Probably should have done it below, huh? Okay. All right. Quantity in the percent formula is the amount of change Oh my gosh, I just did. I should probably read these beforehand. Increase or decrease, or the amount after the change, which I just made a big mess with. Okay, and then the whole percent for whole in the percent formula represents the original amount. Boy, oh boy, I'm going to read it next time. Okay, that is 15 minutes and 10 seconds as I speak. So now, how about that being the end? Okay, all right. I'll see you in lesson 5.